In this video, we discuss impedance and admittance. Let's review the voltage and current relationship for resistor, inductor, and capacitors. In time domain, we know for resistor, the voltage is proportional to the current. And for inductors and capacitor, there will be derivative involved. That is the time domain. If we look at a frequency domain or phasor domain, we can see that the voltage and the current are proportional to each other by a complex scalar. We're going to introduce impedance, that's Z, that equals to the ratio of V divided by I, and V, this is a phasor, and I, that's phasor as well. Therefore, in phasor domain, the voltage, which is a phasor, equals to impedance multiplied by the phasor of the current. If we look at the voltage-current relationship for the resistors, inductors, and capacitors, and compare those with this formula V equals to impedance multiplied by I, we can figure out the impedance. The impedance for the resistor is Z equals to R. For inductor is equals to J omega L. For capacitor is Z equals 1 over J omega C. And this also equals minus J divided by omega C because 1 over J equals to minus J. Once we obtain the impedance, we can obtain the admittance, which is the inverse of the impedance. Notation of admittance is Y. The notation of impedance is Z. So Y equals 1 over Z. For resistors, the admittance is 1 over R. For inductor is 1 over J omega L. For capacitor, the admittance is Y equals to J omega C. It is important to realize that the impedance depends on the value of the frequency. For example, the inductor, the impedance is J omega L is a function of omega. Omega is angular frequency. When omega equals 0, that corresponding to the case of DC circuit. In this case, the impedance of the inductor equals 0 because J omega L, when omega equals 0, Z equals 0. So when Z equals 0, that means in the circuit is a short circuit, is an ideal wire without any resistance. When omega goes to infinity, the impedance goes to infinity. So therefore, in the circuit is open circuit. For the capacitor, at the DC is open circuit. At high frequency, that's short circuit. From chapter 6, we know that for DC, the capacitor is considered as open circuit. And for inductor, the DC in DC circuit is short circuit. The impedance contains the real part, imaginary part. The real part we use R to represent the real part. The imaginary part we use X. The real part is also referred as resistance. The imaginary part is referred as reactance. When the imaginary part is positive, we say this impedance is inductive. When the imaginary part is negative, called the impedance is capacitive. Because we know the impedance for the inductor, J omega L, the impedance for the capacitor is Z equals 1 over J omega C. That equals to minus J multiplied by 1 over omega C, because 1 over J equals to minus J. Now let's look at a couple of terminologies for admittance. Admittance, that's Y. That contains the real part, the imaginary part as well. The real part is G, the imaginary part is B. G is called conductance, and B is susceptance. They all have the unit of Siemens, that's 1 over ohm. And remember, Z equals to R plus GX. And using this relationship, the admittance is the inverse of the impedance. We can obtain G and B as a function of R and X. And we obtain this formula